Welcome everybody, I am a teacher from Ilm Online Academy, and in today's video the topic is chemical energetics. This is basically the chapter 7 of the ongoing series for the chemistry 0620 revision notes, and in today's video we'll be having a look at the chemical energetics. So further ado, let's just begin it. First, chemical energetics, that is also known as the thermochemistry, and it is the study of the energy changes that occur during the chemical reactions. So we have chemical energetics, that is also known as the thermochemistry, and it is related to the energy changes that occur during the chemical reactions. It focuses on the heat energy that is involved in the chemical processes and how it affects the reactants and the products that we will discuss today in today's topic. So the key concepts in today's lecture will be the physical and the chemical changes. Second, we will discuss about the exothermic and the endothermic reactions. Third, we will talk about the enthalpy change and the activation energy for the reactants and the products in this topic. So we'll talk about the first content of our topic, which is about the physical and the chemical changes first. The physical change. Physical changes do not produce any new chemical substance. No new substance is produced. It is easy to reserve back. And the third point is easy to separate. We can easily separate any physical change through any physical methods. Easily separated. So these are the important points related to the physical change. In a physical change, the substances present remain and no new substances are formed. Physical changes are often easy to reverse. Any mixture that is produced are usually easy to separate in case of a physical change. Only the state is changed in physical changes. The state changes, like maybe from solid to liquid and from liquid to gas, gas from to solid and solid to liquid, like this. This is usually reversible. So the example of the physical changes include, for example, the changing of a state, melting. In case of melting, what happens? Only the state changes, like from solid to liquid. The substance changes its states from solid to the liquid, so this is the process of melting, and this is a chemical change. We can easily reverse it back. Next example of physical changes, making a mixture from two or more substances, and the third will be if you dissolve a solute in a solvent. So all these are the examples of the physical changes, and they are easily reversed back. Easily reversed back, it is observable, and the examples are melting, evaporation, dissolving a solute in a solvent, and the last is making a mixture from the two or more different substances. So all these are related to the physical changes. They involve the heat energy, that changing the state involves also the heat energy. For example, if the solid changes to the liquid, then the temperature increases. So melting a solid takes in heat. It is an endothermic change, and this heat has taken in to overcome the holding the structure together. So melting here is a endothermic process, and evaporation is also an endothermic process. The reverse changes of condensation and freezing are the exothermic one. So all these are the physical changes. Next we will talk about the chemical change. Chemical change is opposite to the physical change. During the chemical reactions, new chemical substances are formed, new products produce during this change. And the second thing is they have different properties as compared to the reactants that are used. So the new products that are formed have different properties just because of the chemical changes. And most of the chemical changes are difficult to reverse back. They may be a signs that a new substance has formed, for example, by seeing the color change. You can say that a new substance is formed by the temperature change, endothermic or exothermic reaction, or by the production of the bubbles. So these are the signs that a new substance is formed. The first sign is color change, temperature change, and the last one is fizzing or effervescence if it is produced. So we should know about the chemical changes. The first one is the major change is that a new substance is made during the chemical reactions. Many reactions, but not all of them, are difficult to reverse. During a chemical reaction, energy can be given out or taken in, and there are many exothermic reactions rather than endothermic reactions. So in case of chemical changes, when new products are formed due to change in temperature, chemical reactions that give a temperature change can be grouped into the two categories. First, we have endothermic reactions, and the second one are the exothermic reactions or exothermic changes. So these are the two categories in which the temperature change is grouped. Exothermic, in which the heat is given out or the thermal energy give out, and in case of endothermic, the heat is usually taken in, like for example melting, evaporation, both are endothermic process. So some examples of the temperature change for the endothermic reactions in which there is a decrease in temperature is photosynthesis. Photosynthesis is an endothermic process, and in case of exothermic, we have different examples, like the reaction of a sodium with the water is an endothermic reaction, and effervescence is produced. So it is a sign that when bubbles or fizzing are produced, so that shows that the exothermic reaction happens here. So this is all about the physical and the chemical changes. Next we will discuss in detail about the exothermic and the endothermic changes. So now we'll talk about the endothermic and the exothermic reactions. In case of exothermic reactions, energy is given out. Energy is given out in the surroundings, and there is an increase in temperature of the surroundings. So in case of exothermic reactions, there is a transfer of thermal energy to the surroundings, leading to an increase in temperature of the surroundings. And exothermic reaction transfer thermal energy to the surroundings, leading to an increase in temperature of the surroundings. For example, we have combustion reactions and neutralization reactions, which are the examples of exothermic. Energy is usually given out from the reactants and the products that are present in our reaction vessel, and when energy is given out, then the temperature of the surrounding increases. So an increase in temperature tells us that this one is the exothermic reaction. For example, combustion and neutralization. When a fuel, for example natural gas, burns in excess air, it produces a large amount of heat. Like when methane reacts with the oxygen, in the presence of oxygen, when methane is burnt, so we have carbon dioxide, CO2, plus water is released, plus a lot of heat is released in case of this combustion reaction. So when methane and oxygen react together, carbon dioxide, water plus heat energy is released, and this heat energy means that the heat is released. However, if not enough air is available for this reaction, it will not produce as much energy, and also it produces carbon monoxide, which is poisonous. So this is about the exothermic reactions. Next we'll talk about the endothermic ones. In case of endothermic reaction, it takes in heat energy, it takes in energy from the surroundings, and when it takes in thermal energy from the surroundings, then the temperature decrease in temperature of the surroundings just because of heat taken in. And the examples that are included in the endothermic reactions are thermal decomposition and photosynthesis. Photosynthesis is also an example of this. And next we have decomposition. Decomposition reactions in which a compound is broken down into different products, then energy is usually taken in for the breakdown of the products that are present there. So this is the endothermic and the exothermic reactions. These are the main points related to these, and we have also the examples of endothermic and the exothermic reactions. So the process that release heat energy to the surroundings are known as exothermic. For example, dissolving a magnesium chloride in water is also an exothermic process, and the thermal energy that is released in these exothermic reaction leading to an increase in temperature, and the surrounding include the reaction mixture in the test tube, the air around the test tube itself, and the thermometer or anything that is dipped into the test tube. So this final point is more important. It is the thermal energy or heat that is transferred to the thermometer that causes a rise in temperature on the thermometer. So when the temperature rises, so that indicates that this one is the exothermic reaction. The process that takes in heat from the surroundings are the endothermic, and the endothermic reactions absorb heat. The heat energy is taken in by the reacting substances, the system that is present there, so it leads to a decrease in temperature. Temperature usually decreases in case of endothermic reactions. So when you try to remember these terms, concentrate on the first letter of the words involved, like we have exothermic. So the first word, you have to concentrate on the first word ex, that means exit. So this is the hint about to remember the exothermic and the endothermic reactions. Next, if we talk about same like this, endothermic, that means the first letters en, that represents the enters. So the heat enters the reaction in case of endothermic and exit out in case of exothermic reaction. So this is the hint about the endothermic and the exothermic reaction. Next, suppose we have the test tube like this in which the reaction is going to happen. So in case of exothermic, first if we talk about exothermic reaction, so what will happen in this test tube? The test tube hot, and heat is usually given out from the substances that are present there. So after some times it will normalize to the room temperature, but once the exothermic reaction happens, it gives out heat. This warms the reaction mixture and heat is usually given out to the surroundings like this. So this is the representation of the exothermic reaction when it happens, and the test tube also feels hot when you touch an exothermic reaction. Next, if we talk about the endo. In case of endothermic reactions, what will happen? In endothermic reactions, it becomes cold because heat is usually taken in from the surroundings. In case of endothermic reaction, this cools the reaction mixture and heat is taken in from the surroundings. So this is the exothermic reaction that gives out heat energy to the surroundings, and an endothermic reaction that takes in thermal energy from the surroundings. Now we'll talk about the reaction pathway diagrams. So now the reaction pathway diagrams, which are used to show the exothermic and the endothermic reactions or changes that happen in different reactions. So this is the diagram that shows the energy levels of the reactants and the products in the chemical reactions and shows whether the reaction is exothermic or the endothermic. So these are the diagrams that are usually used to represent the endothermic and the exothermic reactions by using a diagram. Endothermic and exothermic reactions are shown here by the exothermic and endothermic reactions are shown here by the reaction pathway diagrams. So these diagrams show us the energy of the reactants and the products on the y-axis. So we have the graphs like x-axis and the y-axis. Y-axis is the vertical axis, and on the vertical axis we have, on vertical axis of the graph, we have the energy of the reactants and the products. Energy of reactants and products are shown here on the vertical axis, which is also known as the y-axis. Next, the second point, the reaction pathway, the progress of the reaction is on the horizontal axis like the x-axis. X-axis show us the progress of the reactions. And the last one is about the energy change that is indicated by the arrow upward or downward between the reactants and the products. Like for example, suppose this one is the graph, we have x-axis and we have y-axis. On the y-axis we have the energy of the reactants and the products, and on x-axis we have the progress of the reactions. So if a chemical change happens here like this, so the arrows, the upward and the downward arrows are there to indicate the energy change upward or downward between the reactants and the products. So these are the important points related to the reaction pathway diagrams. And now we'll talk about separately the pathway diagrams for the exothermic first and then for the endothermic reactions. So let's start first with the exothermic reactions. So this is the energy pathway diagram for the exothermic reaction. As you can see here, we have the x-axis and the y-axis. On the y-axis we have the energy of the reactants and the products, and on the x-axis we have the reaction progress for the exothermic change. So this is the example of a reaction. For example, we have methane, the combustion of the methane. Methane is the simplest hydrocarbon. So when methane, that is the main component of the natural gas, when it burns, it reacts with the oxygen, and the products are carbon dioxide and the water vapors. So when methane reacts with the oxygen, then it produces different types of products. Carbon dioxide plus water vapors are released in this combustion reaction. This is the example of exothermic change. So we have reactants here on our reactant side and products are produced here on the product side. So the energy is present here in the kilojoule, and the reaction pathway diagram for this is shown here. So the exothermic reaction, you can see here that the energy of the reactants, as you can see here in the graph starts from the 0 here. We have 1, suppose 2, 3 kilojoule, 4 and 5 kilojoule of energy. So the energy of the reactants are here, suppose I'm supposing it. So this is 3 kilojoule per mole, and you can see here the energy of the reactant which are just 1 kilojoule per mole. So this is the indication that the energy of reactants is higher, as here you can see the energy of reactants is 3 kilojoule per mole and the energy of products are just 1. So in case of exothermic reactions, these are the indications for the reaction pathway diagram for the exothermic reaction, that the energy of reactants are much higher as compared to the products. So just by seeing the diagram you can easily tell that is this for the exothermic or for the endothermic. So the energy of reactants is much higher in case of exothermic reaction, that indicates that type of reactions. And the black arrow you can see here, which represents the release in energy and also the activation energy, and the downward arrow to show that the energy is given out or energy is released. This one is the arrow that show that the energy is usually released in case of exothermic reactions because heat is given out, right? So the heat is given out, the reactants have more energy. So when the exothermic reaction happens, the energy of the reactants give out and into the surroundings, and the temperature of the surrounding increases. When the temperature increases, then products will have now less energy. So I will show you the reactants and the products. We have methane, CH4, and plus we have oxygen gas that are present at the reactant site. When the reaction happens, the energy is given out in the form of heat in the surroundings and the temperature of the surrounding increases. So the energy of the reactants decreases and less energy is now transferred to the products because of exothermic reactions. So products have less energy, so they are presented here, CO2 plus 2H2O. So heat is usually given out. In case of exothermic reactions, reactants have more energy and products have less energy. So this is an indication that this one is the exothermic reaction. Next example, we have the reaction between the we have different reactions. We have neutralization reaction, that is also for the exothermic one. So these are the reactions or the reaction states that shows that the exothermic reactions are lower in energy than reactants, right? So the products are lower in energy than the reactants in case of exothermic one. Now I will show you here about the reaction pathway diagram again. For example, you can see here, this is also the energy diagram for the exothermic reactions. These are the reactants. When reactants react together, what will happen? The energy increases like this, and when the exothermic reaction happens, usually energy is given out. When the energy is given out, then less energy is transferred to the products, then they are lower in energy as compared to the reactants. So in case of exothermic reactions, they are lower in energy. In case as compared to the reactants are much higher in energy than the products are lower in energy. So delta H, as you can see here, that is present here as a negative. This is the energy released during this chemical change, the energy that is released into the surroundings, which is required for the increase in temperature, that is the delta H. And that EA you are seeing here, this one is the activation energy that is required to activate the chemical reaction, to start any type of chemical reaction. So this one is the activation energy. So this is the exothermic reactions, and the example of this one is the combustion, neutralization are the examples of exothermic reactions. We have methane plus oxygen that react together to produce the carbon dioxide and water vapors, and heat energy is also released. So the overall energy released during the chemical reaction you can see here. This is the overall energy released during this chemical reaction, delta H, that is negative. Negative sign is indicated for the exothermic reactions or the exothermic change. Now we'll talk about the pathway diagram for the endothermic reaction. For endothermic reactions, we have the example of the reaction between the nitrogen and the oxygen. It is one of the reactions that takes place in the hot engine when the fuel is burned in the car engines. So for the equation for this one, for this reaction will be nitrogen plus oxygen that reacts and it produces nitrogen monoxide. gas is released usually in case of this reaction. So this is the example of endothermic reaction. Then now I will show you the figure that shows the reaction pathway diagram for this reaction. For example, we have, this is the x-axis and the y-axis for this diagram. Y-axis show the energy of the reactants and the products in kilojoule per mole, and we have the progress of reaction on our horizontal axis on the x-axis. So when the reaction happens, what will happen? This is, suppose this one is the energy for the reactants like this, and in case of this reaction we have reactants nitrogen plus oxygen that react together. As this one is the endothermic reaction, so what will happen here, energy is usually absorbed from the surroundings just because of the endothermic reaction, because usually heat is taken in. When energy is absorbed, the energy of the reactants increases because there is the energy that is present in the reactants plus the energy that is absorbed from the surroundings. So the energy increases. When the energy increases, the graph moves upward. So when the graph moves upwards, now the reactants are converted into the products and they form nitrogen monoxide. Nitrogen monoxide, 2 molecules of nitrogen monoxide is produced. Now you can see here, this arrow represents the energy that is absorbed in this reaction, or the heat that is absorbed here. So when the heat is absorbed, there is energy that is present in the reactants plus the energy that is absorbed from the surroundings. So the energy increases and that energy or heat is transferred to the products. So the products now have more energy. As you can see here, this graph, if I show you with the dotted line, 0, suppose 1, 2, 3, 4, 5. So just 2 kilojoule energy is present in case of reactants, and then that reactants absorb the energy from the surroundings and that energy moves up to the 5 kilojoule. So the products now have 5 kilojoule of energy. So for an endothermic reaction, you can see here the energy of the reactants is lower as compared to the energy of products. Reactants have lower energy and products have more in energy. So these are the key points related to the endothermic reactions. For the reaction pathway diagram, products have more energy, reactants have less energy, and this arrow, as you can see here, this one, the blue arrow on my pathway diagram, that is pointed upward to show that energy is absorbed or energy is taken in. This one, that energy is taken in from the surroundings for the endothermic reaction. So this is the progress of reaction between the nitrogen and the oxygen gas in a hot engine when the fuel is burned in the car engine. So it produces the nitrogen monoxide. Now I will show you the general diagram for the reaction pathway for the endothermic reaction. So the general diagram, as you can see here, the products are higher energy than the reactants. There is a arrow, black arrow, that represents the energy absorbed by the reactants, and when reactants absorb energy, so that energy is transferred to the products. Now products have more energy. So this arrow, the bigger one, that shows the activation energy, and activation energy is required to start any type of chemical reaction. So this is the energy progress diagram for the endothermic reactions, and we have delta H, that is the energy absorbed during these reactions, because that energy is added to the reaction, added into the reactants for the conversion into the product. So that energy is represented with the positive sign. In case of exothermic, delta H is represented by the negative sign just because of that energy is given out from the reactants. But in case of endothermic, delta H is represented by the positive sign because energy is absorbed, energy is added into the reaction for the conversion into the product. So this one is the reaction diagram for the endothermic reactions. Products are higher energy, as you can see here from this diagram, like this. Products are higher energy and reactants are lower energy. when the reactants react, they absorb energy from the surroundings, and when they absorb the energy of the overall reactants increases. That energy is transferred to the products, and now products have more energy. So the endothermic diagram for the endothermic so the energy diagram for the endothermic reaction is given here. The enthalpy change, or the delta H, is represented with the positive sign in case of endothermic, and the enthalpy change in case of exothermic reaction is represented by the negative sign. So now we will talk about the enthalpy and the enthalpy change of the reaction. So this is the simplest definition for the enthalpy. Enthalpy is the thermal energy or the heat content of a system, that is known as enthalpy, and it is represented by the capital H. The transfer of thermal energy or the heat during that reaction is called the enthalpy change, and that is represented by the delta H, and the simple delta means change in, and the H represents the heat content. So when the heat is released from the system to the surroundings, it is known as exothermic reactions, or the exothermic reactions, or the enthalpy of the system decreases, and then delta H is negative in case of exothermic reactions. Why the delta H negative? Because the heat is released from the system to the surroundings. From the system means the heat is released from the reactants that are present there, so the heat decreases from the system to the surroundings. Next we have the endothermic reactions, where the heat is taken in, and in case of endothermic reactions, usually heat is absorbed by the system from the surroundings, and the enthalpy of the system increases because of heat is absorbed. So delta H is positive in case of endothermic reaction. These ideas fit with the arrows that we have shown in the energy diagrams. So the energy is given out or taken in is usually measured in the kilojoules. Kilojoule is the unit that is used for the measurement of the energy of the reactants and the product, and 1 kilojoule means 1 kilojoule is equals to 1000 joules, 1000 joules of energy, and it is usually calculated per mole for the specific reactant or the product. So kilojoule per mole is usually used as the unit for the enthalpy change or the energy of different reactants. So if we talk about the example that we have done in the exothermic reaction, the burning of the methane, I will move towards that. So this one, the reaction between the methane and the oxygen, that is the exothermic reactions, and the delta H for this reaction will be delta H equals minus 728 kilojoules per mole for this reaction. And if we talk about so this one is the enthalpy change for the reaction between the methane and the oxygen. In this reaction between the methane and oxygen, as with all other reactions, bonds are first broken and then new bonds are formed. Like for example, in the methane molecule, this is the structure for the methane, and in this, first the bonds are broken between the carbon and the hydrogen. Carbon atoms are covalently bonded to the hydrogen atoms, and in this methane molecules, this bond between the carbon and hydrogen will break, and in oxygen gas, the atoms are held together as the diatomic molecules like this. And chemical bonds are the forces of attraction between the atoms or the ions. Breaking these bonds require the energy. Energy must be taken in to pull apart these atoms, and breaking bonds takes in energy from the surroundings. So bond breaking is an endothermic process because it requires energy. Energy is taken in from the surroundings. So this one is the endothermic reaction. So this is the bond breaking between the different atoms. So this is the reaction pathway diagram for the progress of reaction between the methane and the oxygen, and this is an endothermic reaction. So what will happen first? First the bond will break between the carbon and hydrogen and oxygen diatomic molecules. When the bonds are break, the atoms are like this. We have carbon, we have hydrogen, and we have oxygen atoms. So these are present there. So when the bonds breaking takes in heat, so the energy of the carbon, hydrogen and oxygen increases, and this is the bond breaking. When these reactants react together and they form a new bond, so bond making gives out energy. So we have carbon dioxide that is produced, that is the product, and as you can see here, this is the bond making and that gives out the energy. So new bonds are formed between the carbon and oxygen to make the carbon dioxide, and between hydrogen and oxygen to make the water. So making these chemical bonds give out energy to the surrounding, bond making in an exothermic process. Some bonds are stronger than the others. They require more energy to break them, but they give out more energy when they are formed. So here are the bonds and the products are stronger than those in the reactant. So overall this reaction gives out energy, heat. So it is an exothermic reaction. So these are the examples of the bond breaking and the formation of the bonds. Now I will tell you about the relationship between the making and the breaking of the bonds. Now the relationship between the making and the breaking of bonds and the energy involved here, that is summarized in this memory aid. I will give you the hint about the memorization or summarization of the relationship between the making and breaking bonds, and also the energy that is involved in the reactions. For example, like we have so this is the hint for the relationship between the making and breaking bonds. Making bonds is exothermic, so making equals exothermic, and breaking the bonds is endothermic. So now you can see here we have this one, making, this one is the M for the making, and making exo. This word is exo, that represents exothermic reactions. Next we have this breaking, B, that represents the breaking, and endo. So mexobendo, endo, that is the endothermic reaction, right? So making is an exothermic. Through this hint you can easily remember which one is exothermic reaction and which one is the endothermic reaction. Making is the exothermic and breaking the bonds is an endothermic reaction, mexobendo. Next we have two reactants, A and B. They react together and form the products which are like this, A to B. So this is plus energy is also released here. So this is the formation of the bond that is formed between A and B. So making the bonds is the exothermic reaction because energy is released, making it an exo. When the bonds are broken down between these, like A and B reactant, when the bond is broken down between, so energy is required to break the bond or to break the forces that are present between them. Energy is always required to break the forces that are present between the two reactants. So breaking the bonds is an endothermic reaction. So this is the summarization or memory aid for the calculating the enthalpy change of the reaction. Making exo and breaking the bonds is an endothermic reaction. Next we will move towards the calculation of the enthalpy change. Now we have done with the making and the breaking bond. Next we'll do the calculating the enthalpy change between the different reactions. Now we'll calculate the enthalpy change for the reaction. So to calculating the enthalpy change or delta H of a reaction, we first list out the bonds in the reactants and also in the product side. So first let's take an example. We will take the combustion reaction between the methane and the oxygen. When methane reacts with oxygen to produce carbon dioxide gas, plus water vapors are released in this, and also energy is given out. So from this equation we can figure out that there are bonds that are there on the reactant side. First we will calculate the bonds or figure out the bonds of the reactant side. We have, you can see here, this one is the structure for the methane molecule. So according to this we have 4 carbon hydrogen bonds that are present in the reactants in case of methane molecule, and in oxygen molecule we have, oxygen is a diatomic, double bonds are present, that is covalently bonded. So 2 oxygen bonds are present in case of reactants. So total we have 4 carbon hydrogen bonds and 2 oxygen bonds are present there. Next we will figure out the bonds on the product side. So 4 carbon hydrogen bonds and 2 oxygen double bonds are present there. Now we'll move towards the product side. On the product side, this is the structure for the carbon dioxide molecule, and according to this you can see here 2 carbon double bond oxygen bonds are there, and in case of water molecule we have 4 hydrogen oxygen bonds. Because why 4? Because 2 molecules of water are produced in this reaction. This is the structure for the water, this is the structure for 1 molecule of water. 2 hydrogen oxygen bonds are there, and so in case of 2 molecules 4 bonds are there. So this one is these are the bonds that are present on the reactant side, and also on the product side we have figured it out. Now we would be given with a table listing with the bond energies. We have some bond energies that are given in your exam, and using this table you can calculate the energies on both sides and use that to calculate the enthalpy change also. So first you can see here on the reactant side, this is a bond breaking. Bond will break and then new bonds are formed. First the bonds will be broken down that are present in the reactants, and then new products or new substances are formed there. So according to that, first I will give you the I will show you the table for the bond energies between the different bonds. So this is the table for the bond energies between the different bonds between carbon hydrogen, oxygen carbon oxygen, hydrogen oxygen, carbon and carbon oxygen. This will be given with your question in your exam, and by using this table we can calculate the energy on both sides. So as we have done here with the bonds, these are the bonds that are present on the reactant side, and these are the bonds that are present on the product side. So you have to multiply the bond energies with these bonds, like as 4 carbon hydrogen bonds are there on the reactant side. So what you will do, you have to multiply 4 with the 435 from the table. So by multiplying it we have the answer, which is 740 kilojoule of energy. And also we have oxygen, 2 oxygen double bonds are there, so you have to multiply the 2 with the 497. This is 497. After multiplying it we have 994 kilojoule of energy. So this is the energy on the reactant side. We have 740 kilojoule and 994 kilojoule. Next we will move towards which comes to our, now you have to add all the energies of the reactants. Like when you add them, 1740 plus 994, then the total will be 2734 kilojoule of energy that is required to break the bonds in the reactants. Next we'll talk about the products where the bonds are formed. The products where the bonds are formed between them. So on the product side we have two carbon double bond with the oxygen, so you have to multiply the 2 with 803, that is for the energy for the carbon oxygen double bond, and after multiplying it we have 1606 kilojoule. You also have to write the units with them, and we have 4 hydrogen oxygen bonds on the product side. So you have to multiply the 4 with the single one, which is 464. After multiplying it we have 1856 kilojoule. By adding to these, now you have a total of 3462 kilojoule of energy, which is the total energy that is required, or the energy that is given out when the bonds are formed. So this is the total energy on the product side, total energy for the formation of the bonds on the product side. So after doing this, now you have to calculate the enthalpy change. So this one is the total energy that is given out during this reaction, this highlighted one. And here you can see here, this is the total energy that is required, or the total energy that is required for breaking the bonds. So the enthalpy of a reaction, delta H, is the energy change on going from reactants to the products. So for the burning of methane, the enthalpy reaction will be, we have enthalpy reaction. After calculating these, now we have to find out the enthalpy. So enthalpy reaction is, that is equal to the energy difference. So delta H is equal to total energy. This is the formula for calculating the delta H, total energy that is needed or that is required, and you have to minus it with the total energy that is given out, the total energy that is given out in the products, and the total energy that is required or that is needed from the reactants in the exothermic reactions. So the total energy that is needed in this reaction is 2736 kilojoule, and you have to take the difference with the total energy that is given, 3462. So after calculating this, we have delta H, that is minus 726 kilojoule per mole. So the minus sign indicates that this is the exothermic reaction, and it is useful to remember that a combustion reactions are always exothermic, so you have an indication that you have calculated the value correctly. So the important equation to remember when completing these calculations of the enthalpy of reaction is delta H, this one, total energy needed or to break the bonds, minus energy given out when the bonds are formed. So this is how you can calculate the enthalpy change for any reaction. You can calculate for the endothermic as well as for the exothermic. I have done with the example of the exothermic. You can also do it yourself for the endothermic reactions. For the endothermic, this sign will be positive, and when this sign comes positive, then you can say that there is an indication that you have calculated the value correctly. Next, the last topic of today's video, that is about the activation energy. So we'll discuss about the activation energy now. So now activation energy, that is represented by E A, this one. This is the symbol for the activation energy, and this is the minimum energy that collides then the particles must have to trigger a reaction. If the particles have less energy than this amount, then they collide and they will not react. but if they have more energy, they collide, they react, and they produce the product. So this is the activation energy, that is the minimum energy that the colliding particles must have to react for the successful collision and for the production of the products. So next, there are sufficient atoms or fragments of the reactions must be freed for the new bonds to begin forming. Once started, the energy released as the new bonds are formed causes the reaction to continue. Now I will discuss with the reaction pathway diagram for the burning of methane that we have done also. Now we have, this is the energy level diagram, and that shows the activation energy to start the reaction. We have the reactants methane, and we have methane and oxygen react together to form the products, which are methane CH4 plus oxygen react together to form the products carbon dioxide, plus we have water. So this is the activation energy. This one, this arrow, this is the activation energy or the minimum energy that is required, and this one, this is the enthalpy change, delta H, or enthalpy of a reaction, the energy that is here for the reaction. You can see here we have reactants have more energy as compared to the products. Energy is given out, then the products are formed. So delta H is the enthalpy of the reaction for this one to start the chemical reaction between the methane and the oxygen. This is the activation energy. For a chemical reaction to happen, some bonds in the reactants must break before new bonds are formed. That is why all reactions require some activation energy. For the reaction of a sodium and potassium with the water, the activation energy is low and there is enough energy available from the surroundings at the room temperature for the reaction to begin spontaneously. Other exothermic reactions have a higher activation energy. For example, burning of magnesium can be started with the heat from a Bunsen burner. Reactions can be thought of as a result of the collisions between the atoms, molecules, or also the ions. In many of the collisions, the colliding particles do not have the enough energy to react and they just become apart. So a chemical reaction will only happen if the total energy of colliding particles is greater than the required activation energy of the reactions. So this is the activation energy that is represented by the EA. In the previous examples, we have also the activation energy. This one you can see here, this is the activation energy that is required for the reaction to happen. The blue arrow, as you can see on my screen, for the endothermic, and for exothermic we have this one. This is the activation energy that is required, and delta S, that is negative, that is energy that is overall energy that is released here in this reaction, in this exothermic reaction. So in the last, I will sum up all. First, we have read about the physical and the chemical changes. Physical changes are the changes in physical properties, state, or situation of a substance that does not involve a chemical change. Chemical changes are the changes in which new substances or new products are formed. Some chemical and physical changes are exothermic while others are endothermic. Next, we have done with the exothermic and the endothermic reactions. In exothermic reactions, and thermal energy to the surroundings leading to an increase in temperature, and endothermic reaction takes in thermal energy from the surrounding leading to a decrease in the temperature. So the reaction pathway diagram can be used to show the energy changes for both the exothermic and also the endothermic reactions. Next, we done with the enthalpy change, that is the transfer of thermal energy during a reaction. And next we talk about the bond breaking and the bond formation. Bond breaking is an endothermic and formation of the bond is exothermic. And also remember the one hint which I told you in the video for the memorization of the bond breaking and the bond formation. Next, to calculate the delta H, the required formula is delta H is equal to the energy needed to break the bonds minus the energy given out when the bonds are formed. Next, we talk about the activation energy, that is the minimum energy that is required for the reaction to take place. So, energy pathway diagrams that show the delta H, enthalpy change, and the activation energy can be drawn for both the endothermic and also for the exothermic reactions. So, this is done for today, and we are done with the chapter number 7, that is about the chemical energetics, and we have covered all the topics, all the contents that are present in this topic. Hope you understand all this. If you like the content, then please like and subscribe it, and feel free to ask any question in the comment box. We'll meet in the next one.